Hello, everyone. My name is Piers Ridyard. I am the CEO of RDX Works, and this is Dan Hughes, the founder. We are here to discuss some interesting technology / optimization / cryptography that you've discovered recently. And
I wouldn't say recently. I've been working on it about 12 months, but yeah.
have finally validated that the things that you had a hunch would work would actually work, and that we're going to sort of do a bit of a dive into that because I think it's really interesting. But before we actually dive into what the solution is, I think what would be great is to just do a little bit of picture setting, right? Because a lot of the time, we have these conversations where you're like, Piers, the signature size of this is X bytes. And if you do it like this, then it's Y bytes. And I'm like, cool. Both of those sound like really small numbers. I'm not sure why it matters. And so I think the context of big picture to optimization is really interesting. So let's start on that journey.
Okay, cool. So this all revolves around how do you most efficiently get a set of validators or participating replicas to agree on something, right, in a multi-decree voting strategy, right? So if you think about, you've got consensus, and this is it's quite generalized, right? So it's not specific to really anything with Cassandra or PBFT or hot stuff or whatever like that. It's just a more general conversation. There's obviously stuff I've been working on in Cassandra, but it's to do with like how do you do efficient voting locally and also cross shards, right? And it's quite a big thing because there's two main issues that crop up. One is authentication complexity, which is how many votes do I have to process, right? And the second thing is message complexity, which is how many votes are being sent around and how big are those votes, right? So you could kind of think of it, I suppose, in terms of an election. Yeah, your authentication complexity is how many people have voted in the populace, and somebody's got to verify that all those votes are valid and there's not double voting and all that kind of stuff. And then your message complexity is, okay, you've got this volume of ballots in all of these polling stations, and you've potentially got to move them around in various places so that you can actually tally them, right? So, stick them all in a big van, and that van drives off somewhere where there's a bunch of people that authenticate all the votes. And you have the same thing in like consensus systems. Yeah, you've got these participants that are voting, which are your population, and then the internet are your vans taking these votes from place to place, right? And as you would see in any election, the more population there is in a particular region or country, then the longer it takes for you to count the votes, right? Like when we have an election in the UK, we get our results quite a bit quicker than when they have an election in the US because there's more people voting, right? You've got to move more stuff around, etc., etc. So what you want to have in a decentralized network is obviously you want to have a lot of people that are voting their opinion, right? Whether that's in a permissionless way, like with proof of work, where the proof of work itself is the vote, and so you've got a lot of miners, right, or instances of miners, so machines and stuff that are generated hash power, or if you, and that's like a single decree, right, mechanism where your proof of work is your vote, and nobody votes to agree on that. It's just seen as it's a kind of self-proving. I have the right to vote because mine is the best,
right?
And then you have these multi-decree systems where you have a set of validators that have to come to some quorum agreement on what's happened. And so
I really like the voting station analogy because I think you can actually extend it, right? We can say, well, in a country, we have two forms of trust, right? One is we trust that there is a central authority that will tally up the total, right? Whereas in these networks, we don't. So what you end up having to do is convince each of the voting stations what the total vote is. They know what their vote is. They counted all their votes, but then they need to receive, and like in the most extreme form of it, you actually send, copies of all of the votes that were at each voting station. You load them into vans and you send them to each voting station. So each voting station has its own complete view, and it does the count in itself to validate that that it's valid. In another format of it, each voting station sends its count to each voting station. So now each voting station has its own copy, but you still have to load it into, if there's 20 voting stations, that's 20 vans you've got to load for each voting station. So it's 20 times 20, which gives you how many vans need to move around so that each voting station has its own view. Which sort of starts to give you the idea of the complexity of the problem.
Sure, yeah. And in kind of leader-based systems, you have this central authority in what you just said, right? I mean, it's not a central authority, but there's a pinch point, right? If that leader is faulty or it goes offline or whatever, then, well, who's going to count the votes then, right? So then you have to elect somebody else to count the votes, and then they get elected. And then in leaderless systems, then you have the exploding complexity then of, well, okay, we need a shitload of vans and we need to copy all of these votes into all these vans and send them all off, and everybody counts the votes and everybody comes to the same conclusion, etc. And that's really where things like authentication and message complexity really become quite a problem, is more so in the leaderless systems. You still have it to some degree in systems that have a leader, but it's generally an order of magnitude less. But it can still become a problem if you have too many participants and you're not voting in the most efficient way, and you're not transporting these votes in the most efficient way as well. So and then when you add shards, you can think about shards as being different countries, right? So it's like, we're going to elect who the president of the EU is, for example, right? Now, obviously, the populations of those countries don't actually get involved in that. It's kind of delegated as such. But you imagine if the populations were, right, then you've got 100, 200, 300 million-ish people all voting from different countries on who the president of the EU for those countries is going to be, right? The numbers just start to get silly then. You're not using vans anymore. You're sending planes around, and obviously planes take longer than vans because the distance is greater. So you can kind of take these concepts of what happened in distributed systems, and you can quite nicely boil them down to elections, because that's essentially what's happening, right? Voting and stuff like that. And the only difference is, of course, is that in distributed systems, you're potentially voting on something thousands of times a second, because all these different things that are happening that you need to cast a vote on. Whereas, thankfully, we only have an election periodically.
Right, every 4 years.
Yeah, otherwise, most of the world's carbon footprint would be vans driving around with ballot papers stuffed to the brim. So, I mean, hopefully that paints a little bit of a picture of why these things are difficult.
Right.
And so, one of the things that I've been looking at quite a lot over the past 12 months or so is how can you really make that process efficient, right? How can you reduce the number of vans that are driving around, and how can you also reduce the number of ballot papers in those vans that are driving around, essentially, right? So, like, if you could just give a guy on a bicycle a piece of paper and tell him, okay, you go over to the next town and drop that off, that's more efficient, right? In terms of carbon footprint, road wear and tear, getting stuck in traffic and just zip around it, whatever, right? So I'm kind of looking for the bike on the bicycle, but the bicycle's really fast.
Right. But crucially, without reducing your trust assumptions or increasing your trust assumptions, depending on which way you want to
that single envelope that guy on the bike delivers in its own right is a verifiable proof of 100,000 ballot papers, for example.
Right.
And if there's any queries about the validity of that, then you can send a van, right? It's like, I don't believe that. Okay, well, here's a van. You pay for the van. I'll send you the van full of ballot papers, and you can count them yourself if you want to. So, I mean, and like you may get that in some occasions in distributed systems, right? So if you can send just a compact proof, then there may be some issue, right? The person you're sending to has a different view of what's happened. So even though they can validate your proof, it's like, well, this doesn't actually match what I'm seeing. So then you have to send the vans, right? But then there's as long as only a few vans are going around, because only a few of the counting houses are having a different view, then your overall efficiency of the network doesn't drop much.
Right. So, if you've got 1,000 votes happening a minute, maybe 1 in 1,000 requires a van, but the rest can be bikes.
So that's okay, right? And because of the fault tolerant nature of these systems, it doesn't matter so much if that one is latent, because you can still form a quorum from the rest, right? So if you've got 100 that are voting, and 10 of them are like, hold on, I need a van for this. Well, that's okay. You can still form a quorum from 67. So they'll be a little bit latent, but eventually, they'll get the van of ballot papers, and they'll be like, this is what I'm missing. Okay, I can correct myself, and now I can take part again. And then you can just use the normal healthy process of sending a guy in the back. So I think that analogy has been done to death. So let's actually get into what this is all about. Right?
So why is let's just talk. So removing the analogy, let's just talk about, the vans are essentially internet bandwidth between nodes. And I think most people who, sit at home and don't run servers and just have computers, and they're like, well, why is bandwidth the problem? I don't get charged. I pay for my bandwidth for my internet service provider, but it's actually just like the amount of data I download. And generally speaking, it seems to be like gigabytes and gigabytes. Why would bandwidth be a problem?
Yeah. So the problem is that if you have a very crude voting system, right? So I want to vote on something, or I need to vote on something, and I need to let everybody else know in the network what my opinion is about this thing, right? Then I construct my vote, and so then I need to basically communicate that to everyone, right? So if it's just me and you in the network, it's quite efficient, right? I create my vote and I send it to you. You've got to vote for something, you send it to me, and we're just doing this one-way thing, right? That's not too much of an issue. The message complexity is one, right? And the authentication complexity is also one, because it's just me and you swapping votes. Yeah, we're not very fault tolerant, because if you go offline, then I can't validate anything. I can't make any progress. So if you have more validators, though, more participants that are swapping votes, then it starts to what you end up with is a quadratic message authentication and complexity curve, right? Because then if we had 10 people in, then I then have to send my vote to 10 people, and those other 10 people then have to send their vote to 10 other people. And so very quickly you start to get this, there's tens of thousands, if not hundreds of thousands of messages and votes flying around the network, right? Now in the case of a distributed system, where you want a healthy number of participants, let's say there's 100, right? Then I've got to send my vote to 100 people, and those 100 people have also got to send their vote to 100 people. So then you're at 10,000 messages that are flying around for just one thing, right? Now, where bandwidth gets important is that there is kind of, there's an ultimate lower bound of how small a vote can be, depending on what you're using. In terms of your signature primitives and stuff. But if we just take, standard elliptic curve signature that, say, Bitcoin uses, then your signature is about 65 bytes, and you need to say what you're signing, right? So a hash as well. So you're looking at 32 bytes for the hash, and then maybe, a couple of bytes to say what your opinion is. Is it good? Is it bad? Some error code if it's bad, whatever. So, but you're basically looking at about 100 bytes, right? So I've got to send my vote, which is 100 bytes, out to 100 people. So I've used 10 kilobytes of upload bandwidth. Right? This is just for one thing, yeah? This is just one TPS. I'm sending out 10 kilobytes a second to the network. But then everybody else in the network is also doing the same thing at one TPS. So there's 100 times 10 kilobytes actually being transmitted around in the network, yeah? So then you're at 10 megabytes at that point of bandwidth. 1 megabyte bandwidth. So 100 times 100, 10,000, 1 megabyte, right? So you got 1 megabyte of bandwidth being consumed as a whole by the network just for one thing. So then if you think about, well, okay, if I've got a network that wants to be running at, say, 100 TPS, then the network is going to be consuming 100 megabytes of bandwidth per second collectively. 100 megabytes, right? That's almost a gigabit of information, just votes being sent around to everybody to vote on 100 things per second, let alone any other overhead that you have, right? In terms of, well, what's actually going to happen next, right? And any failure cases, because your failure cases generally use more communication, right? I've failed. I'm maybe missing something that you have that I don't. Can we figure out what that is? Okay, well, I've got this and you've got that, blah, 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 blah. And he sends a message backwards and forwards, and then eventually one or the other figures out where they're wrong. But then also, you've also got authentication complexity, right? So we sent all the messages around, and now I've got to validate those votes. So I've received 100 votes for 100 things. So I've got to validate 10,000 signatures per second just for 100 TPS. Now, it's doable. Like it's not very efficient, but it's doable. But then if you bump it up to 1,000 TPS, then it starts to become fairly impractical, right? Because now you've got millions of messages going around, multiple gigabits of bandwidth being consumed across the network, potentially millions of signatures to validate per second, and it's just not viable, right? You just can't do it. And so that's why you get these exponent curves, right?
Right.
I mean, it doesn't work. And so you ultimately have, in these kind of crude voting systems, you have a cap on how many participants you can have in the network and how many things per second you can vote upon. And usually you're kind of trading off one for the other, right? It's like, well, if I want to be able to have a very high throughput and a very low latency, then I'm going to reduce the number of validators so that I can get more and more throughput, right? Because then I'm having to send votes to less people, so I can send more votes more frequently for more things, right?
This is the EOS method, right?
EOS, and I think Solana also has a reduced validator set, like a bunch do, right? So if I go from say 100 to say 20 validators, then the amount of throughput I can achieve that also increases exponentially, right? It's not linear. So if I have a network of 100 validators, I'm sending a total of 10,000 in terms of authentication complexity. But if I have 20, then I'm only sending around 400. I only have a 400 messaging authentication complexity. So it's an exponent less, right? It's not like, oh, well, I've reduced the number of validators by 5, so my authentication drops down to 2,000. No, it drops down to 400. And so I have a 20x improvement in terms of my throughput that I can do. Right? So I can go from 1,000 to 20,000. But then reducing the validator set size, then, well, you compromise your decentralization, you compromise potential security, you compromise fault tolerance and stuff. And this is kind of part of the whole Zamfir's triangle, right? The trilemma. Yeah.
Right.
If I'm trading out decentralization and security and the population of our validator sets for throughput, then there's these levers that you're pulling. And so what if you have a more efficient voting mechanism, right? So this is where BLS comes into it. Now, what BLS is, for the kind of high level view, is instead of me having to send around, say, 10 different signatures for 10 different things that are happening, I can aggregate those signatures. So I can say, okay, this single signature represents these 10 things that I'm signing, or these 20 things or 30 things or whatever, right? And then you are doing the same, and everybody else is doing the same. So your complexity of message and signatures is much reduced, right? Because now you're not sending out 100 signatures for 100 transactions. You're only sending out 3 or 5 or whatever, right? Much reduced. Right. And that translates to an exponential reduction in your bandwidth and authentication complexity, in the same way as reducing the number of validators.
So in this in this example, just so like, and correct me if I'm wrong on any of these sort of like points. So the first thing that you know as a validator in the network is generally you know what the signatures of the other validators are, right? You know what the public keys of the other validators are.
Yeah, you know the identifiable.
You know the identifiable, right? So what, like, instead of what you can assume here is you can go, if I'm past a signature that is aggregated, I don't have to have been past all the individual signatures because I know who all of the potential signers in the network are. So I can then go, well, which signatures are in this package? Or you can say, you can have a much smaller piece of information that says all of the nodes, but not their public keys and not their signatures. You can then just go, okay, this package, does it actually contain nodes 5, 7, 9, and 24?
Wow. That's a problem. It is a problem, right? So,
okay.
And this is if you look at the way that Ethereum 2 is using BLS signatures, right? Then this is a problem that Vitalik has written about in his blog post talking about this stuff. So let's say we've got these 100 validators still, and I know who all the 100 validators are, right? I've got some identifiable information, and there's some vote power associated with those identities, right? Maybe stake, how much stake they have, and that corresponds to how heavy their vote is. But if I just receive a aggregated signature, then I've got a signature and I've got a hash that it's signing, right? Now, with BLS, that hash can be a combination of different messages, right? So with BLS, I can say I can aggregate the signatures and I can also aggregate messages, right? So I can say this hash represents these messages, and this collective group of different messages has been signed by this aggregated group of validators, right? Gets a little bit complicated. You don't need to worry about it too much. I mean, it's a nice rabbit hole to go and dive down if you want to learn a bit more. But the problem is that the messages, let's just forget the messages for a minute, right? So we just got the same message that's been signed by a bunch of people, right? And I've got this signature. So the problem is that even though I know who those 100 participants might be, I have no information that actually tells me who has signed, right? Because some of them may be offline, some of them may be faulty, some of them may be latent and not signed anything. So I've got this single signature that carries no information with it about which of those 100 has actually signed this. So if I just take that full 100 and aggregate those identities to validate this signature, it might fail because number 99 wasn't around, right? Well, then how do I find out that number 99 is around? Right. Well, do I then do 100 different combinations to try and figure out that Mr. 99 wasn't there? Well, that's inefficient. You end up being more computationally expensive. Your authentication complexity goes up above what the crude method is, right?
Right. So you have a very large, like trying to break a combination lock with 100 different.
You get brute force in it, right? So it doesn't work. So you can go, okay, well, I can send some compact information along with that signature that tells whoever wants to verify it who signed it, right? Which is essentially what Ethereum 2 is doing. So you get a signature that's an aggregate of signatures,
right? And
then you get some meta information which says which validators or which participants are the constituents of that signature, right? But the issue there is that if you've got thousands and thousands of participants, validators, then that metadata can be quite large, right? Even your most efficient cuckoo filters or Bloom filters or whatever, it can still be in the order of kilobytes, right? So you're kind of back to the message complexity, or at least your bandwidth consumption, right? You've got a few messages, but they're big now, right? So again, you're draining your bandwidth,
right?
And there's a lot of kind of really smart thinking and ways to optimize this, the way that Ethereum 2.0 is doing it, but it's complicated, right? There's a lot of complexity in there, and there's a bunch of different moving parts, and if something goes wrong, then you've got additional complexity to figure out what went wrong, right? Why doesn't this signature validate? Is the metadata corrupted? Is the signature corrupted? Is it just somebody being an asshole and just sending me junk? It's really expensive to figure it out. So this is where the state vote model came in, right? So looking at BLS and trying to figure out okay, how would you make this actually efficient? Because in the worst case right now, using this crude mechanism of BLS, we're back to almost the same as what the crude, just send a signature for everything to everybody, right? Almost back to the same levels of complexity in the worst cases.
It's better, but it's not a lot better.
It's better, but it's not a lot. But then if I'm an attacker, then there's potential leverage there I can use to just slow the network down.
Because I can force computation into every single operation, right?
Yeah.
Okay.
Or I can just take an aggregate signature that I've received, aggregate my signature on there, but not update the metadata. And then everybody goes, oh, this doesn't validate anymore. Then you really simple, right? Like there's a lot of complexity around solutions for those kind of attacks that Ethereum 2 is doing, but it's just lots of edge cases and lots of different bits and pieces.
Right.
So, because I got no reference point as a validator to be able to objectively say this signature is junk and the person that sent it to me is malicious, right? Mm-hmm. Because I don't have any information, any systemic information that allows me to be able to look at this signature and say, no, that's junk. That doesn't validate. That's wrong. And then when you include multiple messages being able to be signed by an aggregate signature, then you need additional meta information to say which messages are contained in this hash and which validators are contained in this signature, and then it just explodes. So obviously I wasn't happy with that, because you know me very well, Piers. And I was like, that's not good enough for me. So
not elegant enough. You have.
It's not even elegant enough. It's just not good enough. Like
but I always like the fingerprint of Dan's work for me is always like the end state has to be elegant and simple. Like from the point of view of the mechanics of how it works for the network as a whole. Like that always seems to be what you end up with.
I mean, like there's some nuances, right? So it can be elegant but not good.
Right.
Yeah. So it can be. There's many times when you look at something and you say, you know what, that's really elegant. It's really compact and simple. It doesn't get the job done in the way it needs to.
And then you have things like, proof of work and Nakamoto consensus, which is like very. It's sort of very
that's
rough and
elegant.
ready. Yes, it's
elegant. The solution, like the philosophy of what it's doing is very elegant, right? And when you break it down to its fundamentals, it's also very simple.
Yeah,
but it has problems, right? It can't scale. It's energy hungry in terms of power and stuff like that, right? So it's good, but it's not good enough, even though it's extremely elegant.
It always struck me as brutal. Like it's sort of like it's simple, but it's brutal. It's like a sledgehammer. It's like no,
I kind of disagree.
Interesting.
Like, Satoshi there is killing multiple birds with a single throw of a single stone.
Yeah,
right?
Yeah.
But stone is the stone's big. Okay, it's like so it's going to kill a lot of birds, but it's still quite elegant. If I just throw this stone hard enough, hash power. Then I'm gonna destroy a flock of birds, basically.
Right.
You can argue if you think
tangent
is elegant or not.
Tangent.
It became kind of evident that BLS is not a silver bullet here, right? It's not just you do this and then all your scalability problems and decentralization problems and security problems are dealt with, right?
Right.
BLS it complements something. That's really what I've come to understand. Right? On its own, it's difficult to do anything useful with. You need to have it complement something. You've got this thing, and adding BLS to that makes this thing way better than.
And for reference, what is BLS?
So BLS is a signature aggregation. Well, it's a signature primitive, and some of the interesting features you can have with it are you can aggregate signatures and you can aggregate messages and do both, right? It can also serve as a threshold signature scheme as well, where N of M have to have signed this thing, right?
Right.
And it's really quite flexible. It's a deterministic signature mechanism, so you don't need any random elements and stuff. The random element is the message you're signing and your public key. It's not perfect, but there's no signature scheme that's perfect anyway. So,
and it's a relatively new one from a cryptography point of view, right?
It's quite new. It was invented by 3 cryptographic powerhouses, let's say. I'm not going to try and pronounce all the names correctly. I mean, yeah, it's got a huge amount of potential.
Surnames, right? So BLS is each of their surnames.
Yeah, it's the initials of their names. Yeah. And it's like it's kind of turned into one of those things like snarks a little bit, like everything's a nail, and it's like maybe BLS isn't a hammer, right? Maybe BLS is a different tool that you use in a different way, right?
Is a ruler.
Yeah, you don't need a nail. You need to smack a nail in with it, right? Like BLS is maybe the wall, and then you smash a nail into it later on. So I just spent a lot of time thinking about, okay, like how would you actually use this and leverage to the maximum the properties that it has in terms of these aggregated signatures, right? It's extremely desirable to be able to have a single signature that's 100 bytes long, and that single signature represents tens of thousands of opinions on a particular thing, right? Extremely desirable to have that. But then what other implementations that I've seen so far, maybe there's others I haven't seen that don't have this Achilles heel as such, is the issue is that you're signing stuff that from any particular point of view is subjective, right? That's the issue. So I get a signature, but the person who created that signature of these aggregated opinions has a subjective view of the network at any moment in time, right? Because they may be missing information, they haven't received messages yet, they're latent, they've got corrupted data, whatever it is. It's completely subjective. When I receive that, I have a different subjective view, right? And so it's very difficult for me to use that unless I've been given a bunch of information about the subjectivity that particular validator has, right? And obviously that it's information, so it takes up space. So I was looking at this from the other point of view. Okay, is there some objective piece of information? Is there some objective primitive that is being used or generated or processed or whatever in a set of validators whereby a signature on a particular thing actually isn't completely subjective? Maybe it's weakly subjective, and that's okay, right? If it's completely objective, that's even better. Yeah.
Just for reference, what do those two words actually mean?
What, subjective, weakly subjective, and objective?
Yes.
So objective is that any person that's looking at this piece of information, in this case a signature, right? They don't need any additional information in order to verify it, right? So what I already know, right, assuming that I am non-faulty, what I already know is enough to validate it. Right. Yeah. And even if I'm currently faulty, when I'm no longer faulty, I can look at it again and go, yeah, okay, cool, that's valid.
Right. So if I say, hey, this is my public key and this is a message and I've signed it, you have all of the information that you need to be able to validate that. Is that an example of objective?
Yeah.
Okay.
Yeah. So in the traditional signature thing, it's just you give me a hash, you give me a signature. And even if I haven't seen the thing that you're signing yet, I can still verify that, well, when I see that thing, I can see that Piers has voted for it, right? So I can see it in the future and I know that this is a valid signature, yeah? Right. Whereas with BLS, because it's a collective of things, I don't know who signed it. This is the problem. I don't know who signed it, right?
Right.
And I can't make the assumption that everyone signed it because everybody probably hasn't signed it, right?
And what's the separation between subjective and weakly subjective?
Weakly subjective is that I can come to a partial opinion that this thing is valid, and I can act upon that until it becomes an objective opinion. Right? So I may be missing something, but I can look at something and I can be like, right, okay, so long as I see this thing that's missing at some point in the future, then I can go with the assumption that this is valid.
So in a collection of things, I can know that a bunch of them are correct, and I can wait for some of the subset of those things, but I'm not waiting for the full set to be able to move forwards with some sort of set of assumptions.
Yeah. So I can make some simple decision around, I'm missing some bits, but the rest of this looks good, right? Based on what I know right now. Okay. Whereas subjective is, I have no idea if this is good or not, because it doesn't correlate at all with anything that I know, right? It may in the future, right? Subjective can become objective, but I need more information, basically. Right. Whereas with weakly subjective, I've got enough where I can have a confidence level that is maybe sufficient. And objective is what I know is enough to validate this.
Yeah. My favorite way of thinking about subjective, and again, like, please correct me if I'm wrong on this, is like, let's say that I order the order of transactions I as a node validate is just the order in which I receive them, with no coordination with anyone else. Because different nodes have different latencies, and messages propagate through the network at different speeds, there is no guarantee. It's completely subjective as to what order I'm going to, validate transactions versus any other node, because another node could get A before B and I got B before A. Yeah. And so we're actually not going to be in agreement. We're subjectively in agreement as to which order of things to process in the first place.
Right. And the more things you're receiving and the more participants there are on the network, the probability of two of you sharing that same subjective view reduces, dramatically drops to zero, basically, right, for all intents and purposes. Which is why brute forcing this stuff doesn't work, right? Because there's just too many combinations for you to try and figure out what order was this in, right? Without any additional information, like who signed these things. Now, the nice thing with BLS is that it's not order dependent, right? So I don't need to know the order in which things were signed. I just need to know who signed them, right? Because they're, what's the term? Mathematical term. Commutative, is it, I think? I always bloody forget what it is. It's where you can do two operations in different orders and you get the same result.
Like 1 + 2 - 2 or -2.
Right.
Yeah.
It doesn't matter.
Yeah, it doesn't matter.
1 + 2 is 3. 2 + 1 is 3. Right.
Yeah.
Same thing. So that's handy. So I don't need to know the order, because then BLS would be pretty much essentially useless. Except for the stateful model. Actually, the stateful model wouldn't care about ordering either, because the order is dictated. So the thing I was looking at from the stateful model is, okay, given some proposal, right? So there's a proposal of some transactions that needs to happen, yeah. Then or a sequence of proposals, right? Then there's a defined order in that, right? So if I'm looking at a sequence of proposals that are proposing these transactions should happen next, right? If I agree with that order, with that chain of proposals, then I've got an order, right? Because the proposals are cryptographically secured to tag onto the end of each other. So I can't change the order. The order is defined for me. And if I agree to those proposals because I think they're the best things to do next, then I'm also agreeing to the order in which the transactions are processed within those proposals, right? And anybody else who agrees with that chain of proposals also agrees with the order in which they're going to be processed. Yeah. If they don't agree, I mean, if they agree but they don't process them in that order, they're faulty, and we don't care about their opinion anyway, right? So long as 67% or more of the network is non-faulty and they all agree on the sequence of proposals, then we all have the same order of things, right? So we say, okay, so this is first, that's next, then that, then that, then that, then that, then that, right? Now this is where BLS gets handy. So if I'm looking at these things and I'm executing them, right, I can batch these executions of transaction A, B, C, D, E, F, G. I can say, well, I can batch all of these transactions, and I can say I'm going to vote on the transitions of those things as a batch, right? So I'm going to say, okay, I'm going to create I'm going to vote on that I agree that the transitions of A, B, C, and D are good. So I do some execution, and there's some hashing stuff that goes on, and a Merkle tree gets built, and some other bits and pieces. But the point here is that A, B, C, and D are represented by a hash that I sign, right? And I broadcast that to everybody. Yeah. So we're doing this the other way around here, right? So instead of me trying to reduce how many broadcasts of things I'm sending to people, right? I'm actually saying, well, what I'm going to do is I'm going to change that. I'm still broadcasting to everyone, but the thing I'm broadcasting represents multiple things, right? Whereas before we were saying, I'm going to broadcast a single opinion on something, but I'm going to try and aggregate all the validators together, right? Whereas this way around, we're saying I'm still broadcasting to everyone, like in the initial signature model, but instead of each signature representing one thing, each signature here represents n things, right? Now, when you receive my signature that says I'm Dan and I'm voting for this hash, and there's a little bit of information in there that says what round I'm voting from, right? So it's still very compact. It's still in the order of a BLS signature and a public key. It's about 300 bytes, right? There's some meta information about, this starts at this round and it ends at this round. So you get that signature and you look at what you've got and you say, okay, so I've agreed this. Some time has passed since, so there's a bit more on the end here. But that signature from Dan says it starts here and it ends there. What's okay? So what signatures are in there in the order that I agreed to? A, B, C, D. Okay, cool. So this hash that Dan has sent me, that should, if I Merkleize them, if I put them into a Merkle tree and I execute them, and the execution output, I put that into the Merkle tree as well, I should end up with the same hash as Dan because it's objective, right? If I don't, then either my signature is invalid or you've executed something's faulty somewhere, right? Let's assume for a minute that you're not faulty and I'm not faulty. Then if you look at the output of those A, B, C, and D, because you can see which range my signature represents, and you look at the execution output and you put it into a Merkle tree, you'll get a hash, right? A Merkle root. And so you can then say, okay, yeah, I can validate that, and the signature is valid for that hash. So Dan is voting for A, B, C, and D. So now what I've done is I've reduced my authentication and message complexity by 4, right? Instead of sending 4 things out for A, B, C, and D, I've sent 1 thing out. And you can objectively verify that from your own information because you will have agreed to the same set of proposals. Because if we didn't have a quorum on the proposals, then I wouldn't be voting on them anyway, right? Now you can actually take this much further. So the other part of some of the stakeholder model stuff was trying to find a sweet spot between, okay, how many things can I batch into a single BLS signature where there's like a cross point where it starts to become too late because I've got to wait for these things to execute, right? And what is the minimum bound by which I want to vote on something as well? So if I don't have much to do I want to wait and wait to see more things come in and batch all of those together, or do I just want to fire the signatures out? So the sweet spot tends to be I will either batch things together up to 256 items in a single vote, and if nothing's happening, then I will send out a single vote per second, whatever that batch size is, right? So if only 10 things are happening per second, then I'll just send out a vote once per second, right? Now, if 256 things are happening a second, the size is the same. Right? It costs the same for me to send a single vote out that represents 10 things per second as it does for me to send out a single vote that represents 256 things per second, right? Which is interesting. Your message complexity for those 2 scenarios stays completely flat. Your authentication complexity stays completely flat. So it kind of steps. Every 256 things, you get a slight bump in message complexity and a slight bump in authentication complexity. But I'm able to now send you a single signature with very little additional information that you can objectively verify represents my opinion across up to 256 things. Now, when you apply that to the amount of message complexity bandwidth use, right, from where we started with 100 validators voting on 100 things with a 100 byte message size, the message is a little bit larger here because the signature is a little bit larger, but that message represents 256 times more things, right? So when you actually break it down and you look at, okay, there's gossip going on, these things are being sent around, etc., etc. We go from 100 megabytes of message use down to 2.4 megabytes of message use per item being signed, which is quite a reduction, right? It's like 2%, basically, about 2% of what we started with originally, right?
So obviously like we can keep the assumption in this discussion about the pipelining of the transactions to be processed being objective. Obviously that's a core assumption of this system. And so if it is possible to achieve an objective pipeline of things to be processed by the network, then you can use that as the basis for being able to let people know what should or should not be included in what order, and therefore they're
it's a little bit more subtle than that, actually, right? So the order in which I execute something can be whatever, right? Doesn't matter. I can order it. I can execute things in a completely different order to you, as long as it doesn't violate any state transitions, right? But let's say I've got 256 things that don't touch each other in any way.
Right.
Yeah, they're completely disjoint from each other. I can execute them in whatever order I like.
Non-contentious.
Right? Yeah, non-contentious. What matters is that my vote is constructed adhering to that order that's in the proposals, right? So I can execute them however I want, whenever I want, but when I construct my vote, the blueprint for the order is in the proposals, and we've all agreed on the proposals. So everybody who's non-faulty will create their votes in the same way, right? They will construct them in the same way. They will order them in the same way.
Right.
So I don't need any information other than it's Piers that's signing this thing within this range of votes that I've agreed to, and I can see that Piers has agreed to it too because he voted on those proposals as well.
Right.
Which, in consequence, actually, proposal voting is nowhere near as expensive as state voting, which is we can get into another day. Don't need all this stuff for voting on proposals, because a vote on a particular proposal is implicit for all proposals prior to it, right? So it's efficient there for that reason. So all I need is your vote.
Right. So just so that I'm clear on that one, what you're saying is that you have to strictly vote in order, and if you don't have a piece of information, that's where you stop as an individual
until you've executed it.
Until you've executed,
or until it times out, right? So when my own execution times out, I just put a null in there. Right. If I can't execute it for some reason, I just null. If I execute it and it fails, then I put a different hash there, right? But I always know. And this is where it helps for me to also figure out as a faulty node if you're faulty, right? Because if we're executing the same things, then we should always have the same output, deterministic. Like the execution is deterministic. If you've got the same inputs as me, then you should have the same outputs. So if I get a vote from you that I can't verify because what I'm looking at doesn't correspond with what you voted, then I know that you're faulty, basically, right? It kind of signals me that you're faulty. In the same way, if your vote verifies, and this is the other piece that's nice actually, if your vote verifies against your signature, but your hash doesn't match mine, because then I can say, well, hold on a minute, yeah, this hash it verifies against the signature, but the two hashes look different, right? So either I'm faulty or Piers is faulty. That's when you send the van with the ballot papers around. Right? I said to you, hey, what were your inputs for this? What were your outputs for this? We need to figure out who's faulty here, right? Mm-hmm. The only time I don't have to do that is if I've already got a quorum. If I see a quorum already for those things that have been executed, then I can just give you some information. You say, well, I know I'm not faulty because I can see a quorum here. Here's the quorum that I received. Go and figure it out for yourself. So it's a bit cheaper to do that way. But if these are the kind of different kind of failure cases that you can run into. But what's actually even more interesting here is that I can also just send you just my hash with my signature with no meta information whatsoever, right? I can just say to you, hey, here's my information, right? And you don't need to know anything about anything to like any meta information whatsoever for these state votes, because if our hashes are the same, then you know I've executed the same as you, right? You don't need any of the even even if it's just a small amount of meta information, you don't need that either, right? I can send you the hash and the signature, and if it's the same as yours, we at least know that me and you are in agreement, right? Mm-hmm. So you can say, well, the signature validates, I've also executed it, so me and Dan are in agreement. I don't need to check anything else about that vote. I don't need to go and ask him for anything. I can just check that vote, right? So that further reduces the message and bandwidth complexity by about 20%, right? So now we're down to about 2 megabytes. Now, the problem is that on the other side of this, the authentication complexity is still expensive, because even though I've got a really nice compact way of preserving the order and a Merkle hash to say what I voted upon, so I'm only sending out one message for hundreds of things.
Right.
On your end, you're still receiving hundreds of votes that you have to verify, right? Well, this is where the BLS side of things comes in, right? So if I get a vote from you, and your execution hash in that vote, the Merkle root that represents the execution of A, B, C, D, and what the outputs were, if yours is the same as mine, then I can just aggregate our two signatures together, right? Then I get somebody else who comes over. Oh, his hash is the same as mine, right? And I can just aggregate those signatures together. So I can receive 100 messages, and if all the hashes are the same, then I just can aggregate them to a single signature. Aggregation of BLS signatures is really, really cheap. Right? You can do tens of thousands a second on a single call, right? So if I'm only receiving, say, 100 a second that represents 256 things, my CPU is not even moving, right? You're trying to do that with standard elliptic curve, you're going to be maxing out a core, basically.
Right.
But here, it doesn't. It just blips occasionally. Oh, there's a validation. And so I only have to perform a single signature validation, potentially, for, in this particular example's case, 100 validators voting on 256 things. So it's one signature verification to verify the opinion of 25,600 opinions.
Right.
Just a single one, right? Now, if that signature doesn't validate that I've aggregated, then I can do like a binary, what's it called? It's a bit like a binary search. But I can basically say, okay, this signature didn't validate, right, with all 100 in. So I'll put 50 in one and 50 in the other, right? So if you've got a couple of simplify it. Let's say you've got one that is just faulty, right? That faulty one is going to be on one side, So I'll validate those 50 as one, that'll work. I'll try and validate this one, that'll fail. So I'll split it again, split it again. It gets a bit more complex if you've got a lot of failures. But if you've got a lot of failures, then it's essentially it's a cost you can't get around. But if you've got a lot of failures, then you're probably not getting consensus on proposals and stuff as efficiently anyway. So it's just a cost to bear. Right. But if your network is running healthily within the bounds of F, then that failure cost is fairly insignificant.
Right. So this is just a massively more efficient way of a healthy network progressing with very large numbers of validators with a very high throughput.
A healthy network, but so by healthy here, I'm using the term that there are that F is less than a third, basically. Right. So if F breaches a third faulty, then you have a lot of overhead in terms of validating your signatures and stuff, but you've got a whole host of problems then anyway, right? You've got potentially liveness issues and all other things. So it's not a huge issue if F is quite large, because you're just dealing with a lot of crap at that moment in time anyway. But if it's running fairly healthily, and there's some early out you can do here as well, right? So if I see a hash from you that's different to mine, well, I'm not going to aggregate your signature into the batch log because it's a different hash, right? It's obviously not going to validate.
Right.
Those kind of really expensive failure cases only happen when you're getting signatures for vote hashes that aren't valid, right? So if I'm sending a signature that doesn't correspond to a hash that I'm claiming that it does, then that becomes expensive. But then once I've gone through that binary search, I know someone sent an invalid signature. The only way they would do that is if they were faulty, either broken or malicious. So can I afford to ignore their opinion for a while? Well, yeah, because I've still got 70 other that that are valid.
We can reach quorum without you.
Can reach quorum without you, so we'll ignore you for a while. Right. Occasionally, I'll validate one of your signatures just to see if you're non-faulty again.
Right. Super cool. Well, we better bring it to a close, but thank you so much for that explanation. I hope people enjoyed that. I certainly
I hope it made sense. It was a bit of a brain dump, and it kind of got a bit deeper after the beginning. But I mean, the takeaway is that we don't need any additional information to validate batches of signatures. We can aggregate them very efficiently, and one signature verification can potentially validate the opinions of up to 25,600 state changes. So instead of doing 10,000 validations a second, you're basically doing one.
Right. Awesome. All right, Dan, thank you so much. And until next time.
Indeed.